In this video, I want to quickly go through the idea of a luminosity of a star. So we can start by defining luminosity. Well, luminosity is the total energy emitted by the star per second. Right, so imagine we have a star here. This is what we call a sun. And now imagine there's some imaginary sphere around the sun, like this, right? So to obtain its total energy, we multiply its flux. So if you recall from high school physics or university physics that the flux is the amount of net flow through some area. So we multiply the flux by the entire surface area here. Because imagine we have a imaginary sphere around the sun, right? So if we multiply by what is receiving at each point by the entire sphere, we cover what essentially is the flow of the entire sun at all directions. So the luminosity is going to be the flux per point times the surface area of the sphere. So we need the surface area of a sphere is 4 pi r squared. And in this case, since we want our r to be as close to the sun as possible, so we're just going to define r as the radius, right? Radius of the sun. So this is the radius. So radius of the star. In this case, we're a more general formula. Radius of a star. And then F in this case will be sigma times T to the power of 4. Because remember, in my last video of the black body radiation, I talked about this, that a star's emission, the star's spectrum, the wavelength light it emits is very similar to a black body. So in this case, we can use this as the flux, right? So the luminosity will just be 4 pi r squared times sigma times T to the power of 4. So the luminosity of a star, the total amount of energy, is really dependent on the radius of itself, the radius of the star, and the temperature of the star, which both kind of make sense. So more intuitively, way to look at what we just did is that, as you can see in this diagram, the yellow part is the flux through one piece, right? So in order to obtain the flux, the net flux of the entire sun, or the total amount of energy through the entire sun, we need to have this area and then apply to entire sphere. So that's what we were doing by multiplying by 4 pi r squared, right? So the net flux, as you can see in this image, it says that the flux is equal to flux at surface times the area, the surface of the star, which is equal to luminosity, which in that case would be a ball covered entirely in yellow, with lines going out of it in every direction. If we summarize that all together, the total amount of energy emitted will be this formula right here. So that's the key takeaway, right? So with this formula, we can do a little bit of algebra just to manipulate it, right? So L is equal to 4 pi r squared sigma T to the power of 4. So I forgot to add EFF under the T, which basically means the effective temperature, right? In this case, will be temperature at the surface of a star. So if we just divide if we just move the 4 pi r squared sigma to the other side, we can get the formula for effective temperature. So L divided by 4 pi r squared sigma is going to equal to T to the power of 4 effective temperature, right? Then we just do a little bit of math here. Then we can obtain this formula to the power of 1. 1 over 4 is T, effective temperature, right? So this can tell us the effective temperature, or the temperature at the surface of whatever star we're looking at. So if you're curious, you can go to the Google and search up the luminosity of the sun and then the radius of the sun, then substitute them into this formula, and you can get the effective temperature to be the same as temperature as the surface of the sun if you were to Google it, right? And there's another formula that tells us the flux at a larger distance. Because remember, when we were considering this sphere up here, we're considering our big R to be the radius, right? That's what when we're considering sphere. We're considering so now if I were to ask you, okay, if I increase this big R, right? So if I have a star, and then this is the radius, right? So what about the flux here, like at a distance R? What is that, right? So if there were some distance r, so further away from the star, well, there's a new formula here that gives us Fr is equal to sigma T to the power of 4 T effective temperature over times R big R over R, right? So this formula gives us that the flux, and you can manipulate them if you know. You can manipulate the variables here to obtain R to figure it out, right? This tells us that if you know the distance of R, like let's say you know what exactly this R value is, and you have the radius of the star, you have its effective temperature, it tells you how much flux it receives at that point as well. So in this case, what it also tells us is that the flux depends on the distance of the observer from the star, right? Because this R would be where the observer is. The further away it is, the smaller the flux in this case, mathematically speaking too. So this equation shows that the effect of the dilution of a flux as a function of distance from the star, right? The flux becomes smaller when you get further away from the star. And the human eye has a nonlinear response to light intensity. So for example, that a star might have an observed flux 10 times greater than a neighboring star, but in our eyes, it will not be seen as 10 times brighter than our human eye. That is just how human eyes works. So for this reason, or for practical reasons, ancient astronomers, they divided visible stars into a number of magnitude classes that better measures brightness with respect to human eyes than the flux, right? Because mathematically and scientifically speaking, you should be looking at the flux, but they did it in a way that it was they classify all sorts of different stars into category by how bright they seems to be in respect to our eyes instead of the actual flux. So unfortunately, these astronomers chose an unconventional scale such that the brighter stars have a lower magnitude. I'll show you guys. But first of all, I want to write down this formula for apparent magnitude, right? So the apparent magnitude, so M1 minus M2 is equal to 2.5 log F2 over F1. So what this tells us is that M1 and M2 are apparent magnitude of two different stars or objects in our night sky. And then F2 and F1 is the flux of each one of them. So this really relates the way they define the apparent magnitude with the flux of what is being emitted by the actual object. So this gives a difference of magnitude of two stars as a function of their observed flux. And this formula was specifically chosen so that the two stars will have a flux ratio of 100. If two stars have a flux ratio of 100, they will have a magnitude difference of 5. And again, for historical reasons. So that magnitude decreases when flux increases. I'll show you guys a diagram here. So this is the apparent magnitude of different objects in our night sky. So as you can see, Sun, full moon, Venus, Jupiter. So you can see how this is ranked as sort of brightness, how bright they seem to our human eye. And you might be thinking, okay, so the Sun is much brighter than Saturn, right? Saturn is 0.7 and the Sun is negative 26.73. So it's much brighter. But like naturally or logically speaking, you would assume that if this object is brighter, it will go on a positive scale. But because of the reason how they define it in this case, the more negative or the smaller the apparent magnitude, the brighter the object. So that's how they define the apparent magnitude. So wouldn't it be more convenient to define something called the absolute magnitude? So we define an absolute magnitude as the magnitude at a distance of 10 parsecs. So instead of all these stars having different distance to the Earth, now we have an absolute magnitude for each star that is defined at 10 parsecs. 10 parsecs, by the way. So 10 parsecs. 1 parsec is defined as what? 1 parsec is defined as, so 1 PC is 3.26 light years. So 10 will be 32.6. So 10 PC is 32.6 light year. So this is much more intuitive, right? So instead of having all these stars at different distance from our sun, we have an saying called the absolute magnitude, which is individually defined for each star, an object. It's not really dependent on the distance between us anymore, but and there's a way that we can find this by using a formula called the distance module, which relates to a star's apparent magnitude to its absolute magnitude. So this formula goes as m minus big M. So big M is absolute. This is apparent, right? Is equal to 5 log d over 10. So d is the distance between the observer and the star. So in this case, you could be like looking at Vega, right? You're trying to figure out the absolute magnitude of Vega, and you measure how bright it is. So that's the paramagnitude you measure. And if you know the distance between us and Vega, so then you can calculate the absolute magnitude of Vega. So one example I can ask you guys to do would be to, okay, so now if we know the apparent magnitude of the sun is negative 26.73. So now I ask you to calculate the absolute magnitude. What would you do? Well, we know that the distance from Earth to the sun is 1 AU. So D is going to be equal to 1 AU. So this is the distance between us and the sun, right? It's going to be 1.496 10 to the power of 13 centimeter. So if we convert it into parsecs, which I already define one parsec here, like there's a huge bunch of conversion going on, but you could do it yourself. So this is going to be equal to 4.848 times 10 to the negative 6 parsec. So this is what it's going to be. So now we have D and then we have M. We can figure out the big M, right? So we have the formula M minus M. Big M is equal to 5 log D over 10. So now we know the apparent magnitude as negative 26.73. And then the absolute magnitude, which we're trying to figure out, we don't know. So this is going to be 5 log, distance is what? 4.4848. 10 to the negative 6 parsec over 10 parsecs, right? That's the 10 at the bottom, what is that? Just 10 parsecs. And then if you just move this to the other side, and then you multiply the entire equation by -1 because there's a negative sign in front of M, then you get M is equal to 4.84. So what does this value mean? Well, this value is the apparent magnitude. So imagine you were an observer at a distance of 10 parsecs from the sun. This is the apparent magnitude to that observer, which is at the 10 parsecs of the sun, right? So each star has their own absolute magnitude scale. So that's easier to define because in that case we have something concrete for each star, which is a apparent magnitude defined at 10 parsecs, right? So this is like a basic introduction into what's going on with this apparent stuff and the absolute stuff and how they relate.